Hello, I'm Professor Matt Wiley, and I'll be teaching you statistics this semester. I wanted to start our first lesson to talk about data and some good things to think about. Data is a very interesting subject, something near and dear to my heart as a statistics professor and as a consultant for some statistics firms. But I think that far too often we tend to look at things and we don't stretch our minds. So let me encourage you, particularly in the first couple of weeks of our statistics course, to really think about deleting old ideas and bringing in new ones into your mental program software. So let's take a look at some ideas. First of all, let's suppose that it's raining outside. And I take two squares of same size, I'm not a good artist, but same size butcher paper, and I lay it out on the ground, and I want to see the raindrop patterns that happen. And maybe on one of those squares, I see this. You can draw these a little bigger. I don't know how good that camera is. And then on another one, I see this. And I bring these two sheets of paper in, and then I ask you which one was actually outside and which one was forged. And if we look at this, you'll look at this and say, well, of course, the one on the left is fake. Rain doesn't fall in that sort of a pattern. However, this one on the right, it's a little bit weird because that's how rain falls. But if I circle some pieces of this, notice something. My data, in this case raindrops, seems to come in pairs. It comes in clusters. And maybe the most famous piece of this that we're familiar with is the saying, things come in threes. And they don't come in threes, but they do come, probabilistically speaking, generally, in possibly clusters. Because if everything was evenly spaced, that wouldn't really be random. So that's one of the things we want to think about as we take a look at what data is, what data means, and how can we organize it to understand the world around us better. So let's talk some definitions. First of all, this is called statistics. What is statistics? Well, it's a science. It's the study of data. In particular, we don't want to just study it, but we want to collect it. We want to organize it. And we don't just want to collect and organize it, we'd also like to think about it. We call that analyze. And finally, we want to do something more than just these things. We want to interpret it. We want to explain this to the real world, to real people. And each one of these ideas of what statistics is a piece of what we're going to do this semester. So, our early chapters, we're going to talk about collecting data. We want to think about what is data? How do we collect it? And thinking back to our example of fake and real data, how do we do this well? How do we collect it, but how do we do a good job? Because if we have bad data, no matter how much organization and analysis and interpreting we do later, all we can really say is there's something really bad happening. The first inventor of a calculator, Charles Babbage, he invented a steam-powered calculator, and if you ever get to England, I recommend going to the museum and seeing it. It's crazy. It looks like a steampunk goth. It's very clever. It's a steam-powered calculator. And it was so marvelous at the time that one of the members of the British government asked him, "Mr. Babbage, if you put in the wrong numbers, will it still be able to give us the right answers?" Of course, back in, I don't know, 1800s, 1700s, they didn't know what to do with that kind of stuff. Now we're very much aware, garbage in, garbage out. We want good data. So we're going to talk in the first chapters of our class, what is this data? How do we collect it? How do we do a good job when we do that? Then we want to organize our data. This often means drawing pictures, making charts. How can we distinguish between good ways of organizing our information and bad ways? One of the best things I can ever recommend to people is always study another language. And what comes to mind is in English, I have a cup of coffee here, but it's built out of paper, and so we might call this a coffee cup or something. But if I talked to you about a glass, you would have a strong sense that while it might have the same shape as this overall, it's not made out of paper like this one is. So in English, we organize things, at least cups and drinking objects, we organize them by what they're built out of. A mug is made out of ceramic. A glass is made out of glass. If I talk to you about a crystal vase, you know it's called crystal. There's something different about it that way. In Russian, on the other hand, when you organize drinking vessels, you organize them based on shape. And so that creates a totally different organization structure in your mind. So the way we choose to organize something, pictures or charts or with numbers, it's going to make a big difference to what's happening. Later on, we're going to want to analyze. We're going to be able to tell, is this new stuff really different? Or is it the same as it always was? If I show you that my numbers for this quarter of my company were 2% lower than the numbers for next quarter in my company, would you say, my goodness, this man's a brilliant manager and we should hire him forever? Or would you say, that's the normal amount of iffiness. There's always a little bit of error in our data collection. Let's not give this guy a $1 billion bonus. And lastly, we're focused on interpreting our information. So as we look at information and as we try to collect, organize, analyze, and interpret, let's talk about what we actually mean by this word data. And as always, anytime you go into a math class in college, the cool features of it is that you need to be able to think about new ways of organizing your mind, and to do that we usually require new words. Just like with English versus Russian with the classes. We have to come up with the right words. So, in statistics, we tend to study individuals. Individuals are people just like you and me. However, individuals tend to have things about them, features. You're different than me. I'm different than you. And these differences we call variables. Variables and individuals are different things. Individuals are sort of the containers of our data, where we go and find it, and there's a lot of data contained within me. I have a social security number, I've got bank accounts, I've got credit cards, I have the particular type of watch I'm choosing to wear, and where I live, and work, and play, and how tall I am, and the color of my hair, and my name. You have all these things too, but yours are different than mine. So it's the pieces of information that we have from the individuals that are variables, and it's the variables that we're usually talking about when I say I've got some data. I don't really mean I've got Mike, Sue, and Tom. What I mean is I know Mike's height, I know Tom's height, and I know Sue's height, and now I can figure out that in general, boys are taller than girls. So once you have these variables, there's two real ways that you can split up information with variables. And those are qualitative and quantitative. And what I want you to focus on is these two pieces, the lit part and the end part. Think N for number, and think lit for literature, which means words. Qualitative data is things about me like my name. There's no way I could easily assign a number to my name and expect something good to happen. Now, you might talk about some pieces of astrology, but I'm saying in terms of scientific stuff that we can do with a mathematical chart and formula, my name isn't very numbery. On the other hand, I have my height. And that is definitely a number, and that's a really easy number to compare my height to your height and decide one of us is taller. Whereas if we compared names, it'd be really hard to decide anything other than maybe I come before you or after you, perhaps, in the alphabet. So we've got qualitative data and quantitative data. And of course, in a statistics class where we would like to eventually organize and analyze, we're going to focus on quantitative data. Qualitative's things like stories. It asks questions, how do you feel? And that's important information. Do not get me wrong. Qualitative data is half the picture. But this is an intro stats class, so we're focusing our efforts just a little bit. Once we've focused on this idea of quantitative data, it's time for us to do some interesting organizations. So, let's take a look at some more ways we can do this. I think this statistics definition here is going to go away, and we're going to talk just a little bit about some other ideas. And these ideas are this. Regardless of whether my data is qualitative or quantitative, it doesn't make sense for me to take one story or one number and say that fits everybody. What do I mean by that? I'm Matt Wiley, and that's a piece of qualitative data about me. And I also happen to live in the United States. That's another qualitative data about me. But if I were to decide that every person in the United States' name was Matt Wiley, because that's me, that would be silly. If I wanted to talk about the most common name in the United States, I'd have to look at everybody. So anytime we've got individuals, we sometimes sort those individuals into two categories of people. So this is another organization structure. Remember, collect data and organize it. It's what we do. What we have is we have sample data and we also have population data. And we will always be distinguishing where our individuals came from. Population data is when you talk about everybody. Who has the desired characteristics. Let's say I want to do a study about heart disease, and I decide to focus on white males below the Mason-Dixon line in the United States. Then the population is going to be all white males below the Mason-Dixon line in the United States. That's a lot of dudes. If I then go to my local hospital and find white males, since I happen to live below the Mason-Dixon line, and I find some white males who do this, then my sample would be my local hospital. It's a local group, smaller than the population, it has all the same characteristics, but it's not as many. So we tend to split where our individuals come from, and we talk about whether we were grabbing just some people or all people. You can have all sorts of different populations. They don't have to be everybody in the world. I could talk about all mathematicians in the United States who are 6 foot tall and taller. That would be a population, all mathematicians in the United States who are 6 foot tall and taller. In which case, I would be a sample of one of those. So we tend to find it very easy to grab samples, and this is where we get our data from. Generally. It's really hard to get at population data, because population data are huge. About the only one who can pull it off is the U.S. government census. That's a very large set of data. And it asks lots and lots and lots and lots of people. So we've got our idea of sample versus population, and it would be nice if we could tell the difference between data collected from a sample or data collected from a population. So here it is. This data is called a statistic. This data is called a parameter. So if I talk to you and tell you this is a statistics class, suddenly you say, aha! We're going to be talking about sample data. Sample data that's probably usually quantitative that we grabbed from the variables that individuals have. Now, we're actually going to be focused on this direction. When we talk about interpret, we're usually focused on taking some sample information and figuring out what does that mean for everybody. And you're familiar with this every time you watch a CNN or Fox News 24-hour cable TV channel about the presidential election, which happens every 4 years here in this country. They talk to like 2,500 people and they say, who are you going to vote for? That's sample data, it's statistics, and then they try to use that to say, how are all 300 million Americans going to vote? What's going to be the population decision? And that's what picks whoever goes off to the White House. And we're going to keep on exploring this relationship, so for now, focus on the words. Focus on expanding your thinking, and focus on trying to figure out how do we organize between samples and populations. Let's take a look at a couple other ways that we can organize data. We want quantitative data. It's got numbers, but there's different types of numbers. So even if you have population information, you might have the ability to organize that just a little bit better. So let's talk about some more words as we think about this statistics versus parameters. And don't worry, you're going to keep on seeing statistics and parameters compared and contrasted. Incidentally, side note, compare and contrast. This is the single most powerful tool for you to really master a discipline that you could possibly have. Look at every new piece of knowledge you're given and compare them and see what the similarities are and contrast them. Read and figure out what is the difference between a sample and a parameter. What is the difference between a population and a statistic? Compare and contrast those. Always do that process. It's a very powerful thing. Compare and contrast qualitative and quantitative variables. Try to understand the difference. It's not something that you'll find all that much in the homework, though it will help you do the homework if you can. Instead, it's a mental exercise that you go through that makes you a more powerful student, which makes you a more powerful doer of things. So compare and contrast. But here's what we want to look at. We want to look at what we call levels of measurement. Things like height are quantitative measurement, and we want to be able to distinguish different types of measurement that we've got. At the lowest level, we have what we call nominal. Nominal data is qualitative, and you see the word nom, and that means name, so you've got this idea of a name. My name, Matt Wiley. That's nominal level data. It lets me sort between me and you, because I have my name and you've got yours. But in terms of measuring anything, not so much. It's not very powerful. The next level is called ordinal. Ordinal data has a rank attached to it. But that's all it's got. So it's numbers now. But it's like talking to you about your high school graduation rank. You've got first, second, and third. And definitely that lets us talk about who is the highest student in high school, or who's the most popular, and who's the second most popular person. But ordinal data has a problem it doesn't really make sense to do math on it. If I take the third most popular person and I add the second most popular person into that mix, I don't find myself with the fifth most popular person. That doesn't make sense. So ordinal data organizes people, but it doesn't really have a sense of scale. You know, if I take the third most popular person and double them, do I get the sixth most popular person? No. It can't multiply 3 times 2 and get 6 and have that mean anything with ordinal data. So the next level of data is called interval. And this starts to do what we want. Interval data is very interesting, and for us, we're going to say that the differences between data values are meaningful if we've got interval data. So maybe examples of interval data might be things like, oh, I don't know, I could talk about GPA. Or maybe I could talk about a score on an SAT exam. The SAT is a better one. A real characteristic of interval data is it doesn't have what we call a true zero. So maybe you actually could have 0.00 GPA, and that might actually mean something. You've gone to class and you've got all Fs. So maybe GPA is not the best example there. But SAT scores definitely, because as soon as you write your name on an SAT, you've got some points. So nobody has a 0 on the SATs. Now, just because you write your name down doesn't mean that those points do anything for you, but you've got them there. And if my SAT score is twice as high as my brother's, then I would say that I did twice as well. So this idea of multiplication starts to mean something with interval data. Lastly, maybe, I don't know, another example of interval data might be temperature. In this country, we use degrees Fahrenheit. In other countries, they use degrees Celsius. But whether your freezing point of water is 32 degrees or 0, none of those numbers mean anything because you can go negative. 0 degrees Fahrenheit is a pretty useless number overall. 0 degrees Celsius is cool if you care about water, but what if you add salt into the water? Then it won't work. Am I going to freeze if I walk out in 0 degrees centigrade? No, not so much. So temperature, in general, is an interval data because if it's 100 degrees outside or 50, we'd say it's twice as hot. But it doesn't really have a true 0. The best type of data, the best type of measurement you could impose on something, if we were very, very lucky, would be what we call ratio. Ratio data is stuff that does have a true 0. 0 makes sense. And by true 0, what we really mean is negative numbers don't really work. Things like height or weight. If I was to have a scale right here, and I didn't have anybody on the scale should read 0. And then I could step on it, and the scale would start to read some numbers. So it makes sense to talk about 0 grams, or it makes sense to talk about 200 kilograms. You can have a true 0 there. And if I was trying to lift a 5 kilogram weight or a 10 kilogram weight, I would say that the 10 one was twice as heavy. So you've got this multiplication ability, you've got a real 0, and that makes ratio level data our favorite. Again, compare and contrast. Go and look up some examples, go and read in your book, try to find some ways to compare and contrast nominal, ordinal, interval, and ratio data to themselves, and see what you get. Alright. I think we're getting towards the end of this first section here, so give yourself a shake. I've been talking for, I don't know, 23 minutes or so. We've just got a couple more things to sort through. But before I get into that, let me talk to you about some good habits for a math class. One of the best things you can do when you're trying to study mathematics is practice. And, of course, practice makes perfect and all that good stuff, but what I really mean by this is consistent practice. A lot of people can throw around the word study, and that doesn't mean much. You have to design specific study strategies for you, ones that work for you, ones that make sense, And one of the biggest study strategies that I can recommend is constant study. I look at math, in fact I look at anything that you have to learn in your mind as exactly the same as building your body strong in a gym. And what doesn't work in a gym is it doesn't work to go 1 day a week. They call them weekend warriors, and they're a very interesting group of people to study in terms of how often they damage themselves. And I know that our nursing program here is very interested in looking at that for sports medicine, but weekend warrioring doesn't work in sports, and it certainly doesn't work in math. I would say it probably doesn't work in most disciplines unless you are already quite good at it secretly. Always be thinking about math, but set aside some regular amount of time for you every day to be able to organize yourself and compare and contrast the new ideas of the day or the week and practice the homework and try a couple extra problems. Consistency is going to pay you a lot better reward than simply doing everything Saturday night right before the homework's due. Alright. So, we've organized samples versus populations. We've talked about qualitative versus quantitative. There's one more distinction we're going to make. There's descriptive statistics versus inferential. And with descriptive or inferential statistics, what we're very interested in is being able to describe this side is what we do first. You can draw pictures. You can look at some numbers. Inferential statistics is where you take the sample information, the sample data, and you project it onto the population. This is what we're going to start hitting in the last half of this course. And inferential statistics is where the money is. Inferential statistics is where the real power is. But before we can get there, we have to be able to describe sort of our raw data and take a look at that. So, let's take a look at some raw data. Let's take a peek at what it would look like if we were to start trying to describe some interesting things. And let's see, I guess I will erase all of this so that we've got some areas to look at. So let's talk about samples. Either way, if we're going to describe things, we're probably going to do a sample because it's going to be small enough that we can actually get our hands on it. And later on, when we want to do inferential statistics, we're absolutely going to be taking samples and projecting them onto populations and saying what's happening with the bigger group. So we have to talk about good samples. Remember, good data collection versus bad data collection. The real rain paper versus the fake one. So as you collect sample data, let's talk about what's good and what's not good. The best thing, the gold standard, is called a random sample. This is what happens when the government does the U.S. Census. They look at every house in the entire country. They send out a letter to some of those houses. They pick them at random. And random is a very complicated word, but for now, just imagine that you've got all the house addresses in a hat, and someone's randomly pulled them out without looking. Okay? And then, everyone who gets those letters has to respond. In a perfect random sample, everyone has an equal chance of getting picked, so there's no favorites. And, in addition to no favorites, everyone who's picked has to answer. If you're picked, you talk. Or you're measured or poked or given drugs or whatever the whole process is that we're trying to study here in our sample. You could be doing medicine or who knows what. No favorites, and if you're picked, you're going to talk. Why? Well, what if I pick someone at random and they say, you know, I don't want to talk to you? I'm too busy to answer this telemarketer's survey. That's a problem because then I either have to pick someone else to get the same number of people that I wanted in my random sample, or the person's been allowed to not voice their opinion, and maybe the people who don't want to talk are the people we should be listening to. This is why really the only census that's a true random sample that I can think of in real life off the top of my head is the U.S. Census. It is illegal to not answer that census. And a couple years ago I got picked for the census and they started sending me letters. And I was meaning to get back to them, and so a little bit later than I should have, I replied to one of those letters. And they sent me another letter and said, you've hadn't answered. I'm like, no, I did. And they started calling me, and before you know it, this lady started trying to show up to my door. It was worse than bill collectors. If you're picked, you talk. Now, in general, we have this idea of ethics, and it would be very unethical for me, if I was curious about something, to bang on your door at midnight and demand that you answer it, otherwise I'm going to throw you in jail. But for a perfect random sample, it is essential that everyone respond, and everyone respond truthfully. Random samples aren't always possible. So sometimes we do the next best thing, and we talk about a strata sample. A stratified sample is when we want to make sure that we pick people from all walks of life. And there's all sorts of examples of this, but one of the often things that we talk about is called socioeconomic status, SES. And if you ask people about something, you often care about what income they make. If I decide that we're going to suddenly impose a 50% tax on everyone who earns less than $50,000, I should probably make sure that in my sample I get people who make more than 50K. And I also get people who make less than 50K. And I don't exactly want to talk here about whether we pick equal numbers of each group or how exactly we choose to divvy that up. That's different. But in a stratified sample, there's an idea that we've made this strata, this link. Think of stratified sedimentary rock. It's organized in layers as floodwaters put different levels of it. So stratified samples are split up, maybe based on income. Like I said, socioeconomic status is popular. However, let's say I want to pick how high should the usual doorknob be on a door so that I can open it up and get in. Well, maybe I'd want to do a stratified sample based on height. Or maybe arm length. And it would be very sad if I picked Shaquille O'Neal as the only person who I asked, because that dude's tall. He's going to want to handle, like, I don't know, up here. And I'm going to have to, like, stand on tippy toes to try to get into my door, and that's going to suck. So you can stratify things in different ways, but you get the idea. You want to make sure that you pick some people from each category, no matter how many categories you choose to split things up into doing. You can do systematic sampling. Systematic sampling is when you give everybody a number and you pick everyone after a certain bit. This used to be very popular when you had people lined up in queues. Back in the day, universities loved this. They swore by it because you get all the students on registration day, and you'd have, I don't know, a little table here and a little dude sitting here getting ready to hand out all their class schedules. And you'd have all these students all lined up in a row. And all you had to do was get someone to come up to them with a survey, and all that person had to do was pick, I don't know, every third person. So you count 1, 2, 3, 1, 2, 3, 1, 2, 3, and these are the ones you talk to. That's a systematic sample. For a queue, it's pretty good, it's pretty close to random, and it works pretty well for that kind of scenario. Places where systematic samples don't work so well, what if I have 3 computers that are processing code for me? I guess I just said 3 computers and I just decided that we had more. They're processing code as best they can. And I decide that I want to do a error check to make sure that my computers are doing good code processing. And so I pick every 4th one. 1, 2, 3, 4. These computers live here day in and day out, processing code. If this is the only one I check, if this computer starts doing horrible things, I'm never going to know. I'm doing all my error checking over here. So systematic sample works if you're smart about it, but it doesn't work very good in a machine process at a factory anytime you've got some sort of organization imposed on the system. Next up is a cluster sample. Cluster samples are very interesting. It's when people have already grouped themselves for you. It makes it rather easy to do, but it's not very random. So as I go through this list of samples, be thinking, this is the best, this is a little bit not so good, this is not quite as good as that one, this is worse, and we start getting down into the bargain bin basement of sample methods. So cluster sample, this is when people have pre-grouped. Let's say I do a medical study and I only pick the hospitals in Victoria, Texas to do my study in. That is a cluster sample of geography. Let's say I want to do a study about how students respond to certain teaching methods, and I only pick you, my students. That's a cluster sample. You chose to sign up for my class. There's differences amongst you. I'm not doing anything systematic, I'm just picking on my students, but still there's a problem. You chose to take me. Maybe you knew about me and thought I was awesome. Maybe you knew about me and thought I was easy. I don't think so. Maybe you knew about me and said, you know what, that's the only dude teaching statistics this semester. Have to take him. Boo. Either way, you're pre-grouped. Cluster samples are quite easy to grab usually. They're there. They're already intact. But there's some problems. Because they're pre-grouped, people chose to be here. And that makes you folks different than random people I grab off the street. Namely, you made a choice to show up to a statistics class in some way. Some cluster samples. Next up, we could talk about multi-stage sampling. I don't know, these start to get not so interesting. The idea with multi-stage sampling is maybe you grab a cluster and you get smaller and smaller. So maybe I first start with all my stats students, I analyze some stuff and say, no, that's not quite what I'm trying to find out here, and then I focus on just my online students. Or just my face-to-face Monday, Wednesday, Friday. Or just my face-to-face Tuesday, Thursday, something like that. So this multi-stage sample has this idea that you've got one group that's maybe a little bigger, then it gets a little smaller, then I get a little smaller. Maybe I first pick all my stats students, then I pick only the Monday, Wednesday, Friday ones, then I pick all the ones on Monday, Wednesday, Friday that are doing allied health disciplines only. The problem is, as you go through this process, it's less and less and less random. And random is, of course, always our gold standard. And finally, lowest of the low, a convenience sample. A convenience sample is what happens when you see somebody at the mall with a clipboard and asks you, could you take a minute to answer a question for me? It's definitely convenient, but the problem is everyone who's decided to go to the mall at 6 o'clock on a Friday afternoon is a very specific type of person. Plus, everyone who walks past the person with the clipboard, lots of us say, yeah, I don't have time, I'm busy. So this convenience sample is very easy to collect some data with, but it's also the most rough because these people have selected so much about themselves that it's no longer really random. So you have to be very careful with results that you get from here. So here is how we organize data. Ideally, we organize data that we've collected from a random sample. I've talked to a little bit of everybody from all over the place. Now, when you do a random sample, of course, just like we saw with the rain, that doesn't mean that you don't get little clusters. What it means is you don't just have one cluster. So random samples might look a little clustery at some places. That's okay. things we want to watch out for. We collect data, we want to organize that data. We said we want to collect good data. So these are the things I want you to be thinking about anytime you read a study throughout the whole rest of this semester, but really through the whole rest of your life. Here's what you want to watch out for and be careful with when data happens. There's two things that you can do that would be a little bit unfortunate with your data. So here's an idea. Again, let's think back to that paper, but let's imagine this like some kind of picture frame. Once you've chosen the people to talk to, no matter whether you've chosen it to be random or whether you've chosen it to be a cluster or convenience, no matter what, unfortunately, no matter what the whole population's doing, and I'm drawing a whole bunch of little stick figures here, and all these people outside here just so happen to be happy. But I've chosen to look at the two people because I randomly picked things and it clustered a little bit. I didn't pick a lot of stuff. I picked two people who were sad. These are the people I'm focusing on in my sample. If I accidentally, through random or cluster because I go to, I don't know, a graveyard or something, and no matter what, if I accidentally pick the only sad people in a world full of happy folk, I'm going to naturally start to live inside my frame, and I'm going to forget that there might be other people out there. As I organize and analyze my data, I have to be careful in my frame. So my frame is all the people who I actually end up talking to. And maybe I do get one happy person. And maybe there is a sad person out here. But as you can see in general, in the world at large, there's only 3 sad people and 3, 4, 5 happy people. There's more happy folk than sad. But because of the frame we've chosen, it seems like there's 2 sad people for every 1 happy person. So that's a little bit unfortunate. So, under coverage. Is what happens when we don't look at enough. When we eliminate some population people from our sample. And that's the whole idea of a sample in a sense. You just have to be smart about it. So, we now got 2 final, I think, definitions that I want to give. I want to make sure that I read them the same because everyone has a slightly different bit of English that's going on here. And I need my glasses because that's how it's going. Alright, so I have a sample error. And I have a non-sampling error. A sample error is the difference between the measurements in my sample and the world at large. So this comes even with good samples. The sample is not the population, right? Even if I picked a random sample, I could have accidentally, randomly, grabbed 2 sad people and 1 happy people if I was just going to grab 3 folks in my sample. It could happen. On the other hand, a non-sampling error is what happens when you've got bad data collection, or I've used a bad sample process. Bad data collection. Happy or sad? I'm going to check how many I've got. In this box, as you can see, there's 2 sad people and 1 happy person. Bad data collection. I just made a mistake as to which side I should have recorded this person's feelings. So that can happen. Bad sample process. Maybe I haven't actually picked people at random. Maybe I've just gone and focused in on the only sad people. So these are what we call non-sampling errors, because it's not the fault of the idea of a sample, it's our fault. So this is the stuff that we want to eliminate. You can never get rid of sampling error, but you can keep non-sampling error to be very small or non-existent, as long as you think about random samples, clusters, convenience samples, multi-stage sampling, and be thinking about what are the risks and what are the rewards of certain types of data. Alright, I think we are almost done except for one final list that I want to draw up. So give yourself just a bit of a shake while I eliminate this, and let's talk about study design. So we've mentioned samples versus populations. We've said how to collect a good sample. We've mentioned the difference between sample error, which is inherent to sampling because we're not talking to everybody, versus non-sampling error, which is a fault of bad sample methods. Now we're actually ready to look at how a study works. So let's take a peek. For a stats study, and this is what I'm about to write is gold. If you can understand this and do this, you are capable of marketing yourself for very high levels of salary, and you can make people pretty much pay you whatever you want. So I really do think that statistics is the most wealthy class because it creates the most wealth if you're willing to go for it. So the first thing you have to do is you have to identify, ID, stuff that is cool. Now, I'm sure in your book you can find something clever, but ID stuff that is cool. Find a variable that is interesting. Height probably isn't all that interesting a variable unless you're a basketball player, but there's all sorts of things that are. I drink a lot of coffee in my life. Does that make me have a higher risk of heart attack? That might be an interesting variable to talk about. Once you've ID'd an idea that's cool, specify the variables. You need to figure out, is it qualitative or quantitative data? How are you going to organize it? What's it going to look like? You have to design protocols. What do I mean? When we talked about that example where I had the non-sampling error, if I accidentally coded in happy twice instead of sad twice, you want to be able to organize your data collection so that hopefully there isn't a lot of room for error. Think about ways to double-check the process. Once you've got your variables and data being collected, then you have to decide population or sample. If my population is just students at my college, that's not a very big population. Maybe I can use the whole population, give everyone a survey. Or if my population is everyone in the entire world, well, maybe then I have to commit definitely to a sample. So you've got some differences there. So you have to decide population or sample. It's going to affect the mathematics that we do just a little bit. Talk about security. Depends what you're doing. A lot of my students are allied health, so I want to mention this here. If you're collecting patient data, if you're mentioning how sick someone is, or if you're collecting financial data, people want to know that you're not going to get out there into the great wide world that Matt Wiley is dying of blank and he makes so much money. That wouldn't be cool. I wouldn't feel comfortable answering questions to you if you were going to just randomly put that on a website. So you have to talk about how are you going to keep your data secure. Is it confidential for the patients? All this kind of stuff. So you have to organize that kind of stuff. You also have to talk about ethics. Why are you using this data? Are you collecting information about me so that you can then try to sell me something later on? Is it a good product or a bad product? Some 80% of elderly Americans are scammed over the telephone every year. If we're doing a study to say how to scam old people, that's horribly unethical. Probably violates a lot of this too, but that's a very bad thing to do. So consider the ethics. And that's a black and white example possibly, but focus in. Ask, would I be happy telling my grandmother I was doing this study? That's always a good rule of thumb to discuss with the ethics. Collect the data. Using the correct sampling methods, getting the right protocols, making sure you're not doing something weird like just asking two people who are your friends. Collect the data, and then use either descriptive say or, but and/or inferential stats, to organize and analyze the data, and lastly, explain. Explain using English, simple words, to somebody who knows nothing about statistics, what you've discovered and what you've done. It's very easy to come to me and tell me, look, I've done an ANOVA analysis and we have successfully managed to find mean, median, and mode, and we understand standard deviation and variance, and here is our results, and then throw some number vomit at me. And you could do that to me, and I'd be cool with that. But you need to go find someone who doesn't do statistics. Go find your dog or your little kid brother and sister and explain what happened. And as a side note, that compare and contrast that I talked about earlier as a study method, try to do that with some of your problems. If you can find one of the homework examples that's one of our more in-depth exercises, and if you can at the end of that problem explain to your kid brother or sister, this is what we did, here's why it's cool. If you can do that, you probably understood it. And if you find yourself using vague words or weaseling around some idea, that probably tells you if you can't explain it to somebody who knows nothing about statistics in English, maybe you need to explain it to yourself a little better as well, to try to understand what's happening. Alright, I think that's about good for our first lesson, so I will see you in the next section, and until then, be safe.